This is part 16 in a series of videos in which I'm attempting to reproduce an ADM-3A main PCB. This is the prototype. I've been working my way through various steps of testing, got through to the point where I could start displaying characters on the screen. Notice I don't really have a keyboard here yet. This is just a case of shorting out the pads on the key terminals to simulate pressing keys. But the next step was for me to start testing individual functions. As you know, with a dumb terminal like this, the keys or the character sets are not all printable characters. Quite a few of them are commands. So for example, if we look at the instruction set or the character set for this terminal, you'll see that these two columns are control values and they're accessed by holding down the control key. Of course, these can mostly also be sent in through the RS-232 port as well. And they perform various tasks such as moving the cursor around, beeping the sounder, clearing the screen, things that perform actions but don't result on anything being directly displayed on the screen or sent out as a character that can be printed to the remote computer. So that does mean that the system has to be able to decode the difference between printable characters and values that are used and interpreted as commands. Now on top of that, this unit was designed back in the late 60s, early 70s, and back then there was a massive cost penalty for using ROMs. Now the original design used masked ROMs, and they were in general programmed at the point of manufacture. They were horrendously expensive and quite small capacity, so that quite often resulted in systems like this that had various memory options. Now on top of the mask ROM being expensive, the SRAM chips were also incredibly expensive. Really any sort of memory back then was the major cost in the system, and most likely the cost of the RAM chips and the mask ROM was more than half the overall cost of the board. So there were various options. One of those was to have uppercase display only. The other one was to have various limitations on the commands that could be accessed. And what you did with the options was to fit one or two of the ROMs depending on what options you'd purchased, and that would dictate the number of the SRAM chips that you needed to fit. Now of course we can get them much more easily these days, much more cheaply. ROMs are much larger capacity, and because the original mask ROM was not available, what I've done is change the design slightly. It's one of the few design changes I have made, so that I can use a more modern EEPROM. And not only that, but we can have multiple character sets in the EEPROM. Now one thing I have kind of glossed over in terms of explanations so far, to try and keep things moving along and not get bogged down with the complexities of the way the system works, I've been trying to keep the descriptions as simple as possible and as limited as I can to specific elements of operation. But in this video I just want to quickly describe one of the complications I haven't really mentioned previously, and that was the requirements for the character set for the ROM. Now if we look at the memory system, we'll see that originally there were two mask ROMs. Each of these was 512 bytes, and each byte was 5 bits long, which is ideal for storing 5-bit character sets. The lowercase ROM was an option. When you didn't have it fitted, you could leave a couple of the SRAM chips out as well. But because the system still needed to operate if this wasn't fitted, you couldn't just have a hole in your character set. The way that they access the lowercase versus uppercase is a bit strange, and also bear in mind it's not just a case of ignoring the shift key, because certain characters you still want even if they're not lowercase. So for example, keys like 1, 2, 3 and 4 keys have symbols above them which are accessed through the shift key. They're not uppercase or lowercase characters, but they are accessed through the shift mechanism. So the overall system was organized, and the lowercase mask ROM was accessed by effectively flipping the bit 6 address line. But it didn't always flip it. It kind of depended on what else was going on in the system and whether you needed to access certain characters all the time, or if they were just lowercase characters. So this flipping of a bit, if you're familiar with designing systems, you know that when you flip a bit in a binary system, you effectively map a block of memory into a different address, and that's what we end up with here. If we look at the simplified memory map for this, what we end up with is a lowercase ghost area that's not directly accessed, and it's occupied by the command area, or the command values. We then have the first block of uppercase values, the second block of uppercase values, which may include some shifted characters, and then we have the lowercase characters, and these run from address 0. 1FF is the end of the first block, and then 300 hex is the end of the uppercase characters, and 3FF is the end of the lowercase characters. So we need to take this into account when generating the ROMs to make sure we get the correct characters in the right order. It was further complicated by, for some bizarre reason which I haven't actually seen an explanation for anywhere. If anyone knows why they did this, I'd be interested to hear. Is that they also inverted the address lines in the lowercase ROM. That's why they're fed here from the inverted buffer lines. Now, of course, I can't do that. I can't really have them being driven by two different sets of buffer lines. I could have put a separate buffer in between and gone about it that way. Also, this arrangement up here is what maps the lowercase and uppercase ROMs. But I wanted to have just a single image. I didn't want to start messing about with adding additional hardware. So what I did was just make sure that the blocks of characters were arranged like this, and then just simply reverse the order of the bytes or the byte blocks within the lowercase part of the memory map. You don't want to reverse all the bytes. Each 8 bytes is one of the characters, so you want to reverse the order the characters are in, but keep the same order for the individual bytes within each character. Otherwise you'll end up with the character set being inverted for lowercase characters. So in other words, what you're trying to do is move this character down to here and this character up to here, and basically swap them all around. But you don't want to swap the individual bytes within a character, otherwise you'd end up with a reversed character. Okay, so I've done that. That's the reason I haven't shown lowercase characters up until now. It's quite a complicated thing to do. I had various options at the point when I was designing the replacement ROM, but although this is more complicated to explain, it's something that you don't need extra hardware for. It's just making sure that you're aware of this when you're creating the character sets. So once I've done that, the next thing I wanted to look at was being able to send actual serial data, and to do that, of course, I need to get the serial ports working, and because so far I've been running it on just the 5V rail, then the serial in-out wouldn't work. Although I could use a 5V only version of the UART, the serial line drivers require plus or minus 12 volts. So what I've done is I've wound a transformer that matches the requirements of the original terminal. So if we look at the power supply, then you'll see that there are 4 windings on this transformer. I won't go into this now. It's not plugged in at the moment. It does work. I have tried it, but for test purposes I'm still using the bench supply because there's no real current limiting on the transformer, and I don't yet have any fuses in place, so I'm using the bench supply just to make sure I don't blow anything to pieces. the transformer is fairly easy to wind, but I'll describe that in the next video. What I want to look at in this video is the testing I've been doing for the character set and the control sets. So looking at the schematic for the keyboard, we'll see that firstly I had to make sure that I'd got all these connections right. It's just essentially a matrix of connections, and I needed to make sure that each of the keys was being accessed by the right location on the PCB. Otherwise, if you press the B key, it might be an F or something, so I needed to make sure they were right. I've done all that. I won't show you that, it's obviously tedious. It's just really going to each one and making sure the right character is produced, and then doing the same thing when shifted, and also doing the same thing when using the control key. Once I've done that, and what I'm going to look at in this video is the actual commands themselves. So these are where the value coming from the keyboard is interpreted as a command rather than the printable character. So I'll get the board powered up, and I'll just show you the general way I've been testing this. Okay, powered up. There is a cursor on the display, you can't quite see it, but I'll bring it onto the screen. And to do that, we need to make use of the first commands, and these are commands such as the backspace, line feed, and the VT, which is a vertical step. So to access these, I need to short out the control key on the keyboard, which I've just done, and then I can start trying to access these. And really what I was doing is looking at the keyboard on the original board I have here. But the first one, of course, and again we just short these out to simulate it. Okay, I brought the cursor onto the screen so you can see it a bit more clearly, and all I need to do now is short out the appropriate key. I've got the control key shorted, so it's simulating pressing the control key, and now I can move the cursor around the screen, assuming that the commands work for the cursor control. And these are not printing, of course, these are just causing a command response that's changing the count in the cursor position counters. And as you can see, all four commands work fine. Any that don't work, I could just put a scope on here and then start backtracking, and there'd be an issue here somewhere, or it's possible there could be an issue somewhere in the circuitry that is triggered by these. So the next one I wanted to test was the bell character, and that's just going to produce a beep. Now, producing a beep on a system like this is nowhere near as simple as you might assume it is. You'd think it's just really turning the beeper on and off. You can't do that in a system that has to run in real time. If you've designed embedded systems, you'll know that if you turn a beeper on for a very short time, you'll just get a click. If it's on for a very short time, you won't hear it at all. And you can't just turn it on, wait long enough for someone to hear it. So generally you'll need 20 or 25 milliseconds at least to hear it as a tone or a beep, preferably a bit longer than that. But you can't halt the system for that amount of time, because this is dealing with real data in real time, and you end up missing data or cutting bytes in half if you start just halting the system. So this is quite complex. What it actually does is it turns the sounder on, leaves a counter running for a predetermined length of time, and then it comes back and turns the sounder off. There's a similar thing actually when you press a key. There's a debounce counter as well. So when you first press the key and the key is detected, it starts a timer running, and it's 5 cycles at 900 Hz. It's quite a short timer, but it's long enough to allow the key contacts to settle. If you don't do that, you can end up with a single press on the key giving you multiple characters on the screen as the contacts on the key bounce up and down very quickly. Okay, so now we've got the cursor position commands working. The next thing we can look at is the sounder, and as you can hear, that's working fine. So that's all the circuitry that drives the sounder, the timer for the sounder, and of course the command interpretation for the sounder working as well. What we'll do now is just put a few characters onto the screen. And incidentally, the uppercase, lowercase display of characters is fairly complex on here, and there are various options. You can turn off the handling of lowercase characters completely with one of the option switches, and there's another switch that allows you to turn on and off the display of uppercase characters. It might sound like it's the same thing, but the difference between the two is enabling lowercase allows the system to generate lowercase characters through the serial ports. Turning off the display is slightly different in that the system can still send lowercase characters out through the serial ports, but it won't display them on the screen. Okay, so we'll get a few characters on the screen. And notice now these are all lowercase, which with lowercase enabled by default, the lowercase. If I short out the shift key and then hit the same key again, notice that they're now uppercase. So in other words, that's working fine. The next command I want to look at is the clear screen command, which is quite a complex command. So that's this down here. So firstly, make sure we can detect it, but then also make sure that the clear screen works, because that's quite a complex thing for the system to do. It triggers quite a few different things. It doesn't just clear the memory, it writes zeros to all the memory locations. So that's this key, and we should clear the screen and home the cursor, and indeed that's what's happened. Though you can't see it, the cursor is now at the top corner. So I'll just produce a few characters so you can see the screen again. Okay, so that one works, and this is what I've been doing, just going through and checking that all these work, checking the backspaces work, home works to home the cursor, cursor movements, carriage return. So again, carriage return is a non-printing character. It should just cause the cursor to move back to the start of the current line, which it does. And then of course we have line feed, which just moves the cursor down one line. So I'll move the cursor so you can actually see it. So carriage return and line feed are separate characters, as they are on modern systems. Same with the bell character. Most modern systems, a lot of these characters still exist, if not all of them, and they're interpreted in different ways, but you can still access the original functionality. For example, if you go into the command prompt, then what you can do is type Alt 007 on the numeric keypad, and you'll notice that will give you the same response as typing Control G. And that's exactly the same as what this system does. Control G is the sounder, the bell character, as is 007. And so modern Windows systems still use a very similar system to this. It's just that most of it is hidden in a much more simple interface. Okay, so I've been through all this and they all work, so I can't find any functions so far that don't work. All the instructions work the way they should, all the characters seem to work. I still need to go through and closely examine each one to make sure I haven't made any mistakes when I reverse the character set. That was a fairly tedious process. I could have written a piece of software to do this, but it was a coin toss really, whether it was quicker just to do this by hand or write some software. So I ended up doing it by hand. And it didn't take too long, but I need to make sure that I haven't made any mistakes in that. And then of course, if we want to, we can have a completely separate character set. Now at the moment, because there's nothing in the ROM and it's programmed to all zeros, notice that the alternate character set gives us a blank screen, but it could be an alternate character set if that's what you wanted to do. Okay, so that's it for this video. It was just really going through, making sure all the commands worked, making sure that all the characters print in the way that they should. All the shift characters work, so for example if we take the digit 5, select shift and then hit 5 again, we get the percent symbol, which is the shifted character, but is actually in the uppercase part of the character set. So it's making sure that all these things work and that I'm getting the correct response. Because these characters that are being displayed are going through the UART, we can be fairly confident that if we test them like this, then we can feed these through to the serial port and make sure that what we're sending out is the correct character. So this testing doesn't need to be as extensively redone when we get the serial port working, but at that point it will become much easier to do more in-depth testing. So one other thing that I've been checking is that the various baud rates work. So because we're sending data using the serial clocks through the serial system, then firstly you'll notice that if we don't have any serial clock selected at all, then nothing will happen when you hit a key. I'm currently on 75 baud and we'll hit a key, and so you can see that that's working fine. I'll switch to 19,200 and we'll hit a key again. So notice that is also still working. There's a different key, by the way, so that's why it's a different character. And I've just been going through making sure that all the baud rates give the correct character. We don't get any kind of scrambling or errors when the characters are being sent through. So in other words, the system will work at the various baud rates. Now, someone did ask me if it was possible to increase the speed of the system with regard to baud rate, and I'd have to say it probably isn't. It's worth looking at. It might be a nice experiment, but bear in mind the next stop is to double its speed, and I think trying to run a system like this at twice the speed it's been designed for, especially we've got the UART over here, and then the serial data takes a very convoluted path through to the serial port. I think it's fairly likely it's not going to work reliably at much faster baud rates. Still worth a try if someone wants to give that a try, but it's not something I'll be looking at. I'm really trying to reproduce the original rather than make a modified version. I've only made modifications where it was absolutely necessary. Okay, so that's it for this video. In the next video I will finally get around to seeing if we can send out some actual serial data, hook up the newly wound transformer, put that through its paces, and then we'll be obviously getting very close to the home stretch for this development. Next thing after that will be to look at the actual keyboard. As ever, comments welcome.